In today's lecture we are going to move through our section on path and line integrals. In previous lectures we motivated the study, we looked at the path integral and some applications, and I introduced the line integral or the vector line integral involving vector fields. In today's lecture we are going to look at the applications. So we're going to talk about work, we're going to talk about the flow integral and circulation, and we're also going to talk about flux in the plane. Now think back to last week when we talked about divergence and curl. Divergence measured flux, or the spread of a vector field, and curl measured rotation. We talked about circulation density. So in that lecture I mentioned, somebody mentioned at the end, do we need to know this? Yes, because it relates to the ideas that we are going to see today. So the first application we're going to look at is so-called work. I would expect quite a lot of you to have seen this, the idea of work before, but let me just kind of refresh your memory because you may not have studied any physics. That's not a big deal if you haven't, okay? So when we talk about work, we talk about the energy expended when a force is applied to move an object along a path, a curve. Now, the most simplest case that's, for example, taught at high school is the case when you're moving the object along a straight line from one point to another point, and the applied force is constant. Okay? So the vector F, the vector field F, doesn't depend on time or position or anything like that. It's just a constant vector. Okay? Now, under that setting, it's basically just, to compute the work, it's just the tangential component of the force. So, let's just, this is like the tangential component there in the direction of the vector PQ times the distance PQ. Okay? Now, if we just denote the vector PQ by this vector u, then in a vector sense, this is your sort of tangential component in the direction of motion, and then you just multiply that by the length. So the magnitude or the length of PQ is this. So you get this dot product. Can I have a show of hands? Who has a vague recollection of calculating the work or looking at the work in this context? Okay, a few people. Okay. Don't worry if you haven't seen it. Don't worry if you haven't seen it. Okay, so with the angle here, we know we can write dot products in terms of magnitudes and angles, of course. Okay, so that's the most basic definition of I guess the most basic way of calculating work through movement over a straight line, and the applied force is constant. So our here, let me just remind you, the work's measured in joules. So 1 joule is 1 Newton meter. Okay. Now, our objective today is to look at what happens when the applied force is not necessarily constant and the movement is not necessarily along a straight line. That's the idea for today's this part of the lecture. Okay, so here I've got a curve, a blue curve, which is smooth. In particular, think of a curve path and the applied force not necessarily constant. So, how can we speak of or compute the work done in moving, say, a particle or a body from this point, big A, along this direction up to this point, big B? Well, essentially, all you do is you just integrate the tangential component of your force along the curve. And this is actually just the path integral that we looked at a couple of lectures ago. Okay? So here in the picture, this t, remember, is a unit vector. And we know with vector fields and curves, direction is important. So you can see here that in this picture, the direction would be movement from this point this way up to here, not the other way around. Okay? So we can write it this way, or we can write it this way. This is like a more compact form of a so-called line integral. But essentially, the computation comes down to the following. Okay, so imagine here's the zero vector, and here's the origin, and you sort of parameterize this curve. That's where the R is there. Essentially, it's just the dot product of the vector field along the curve with this tangent vector, R prime. You dot that together and you integrate. Now, if I've got time at the end, I'll give you a little bit more justification of why this actually measures the work. But I'll come back to that if I have time. Okay, so suppose I've got a vector field and a smooth curve, or a smooth parameterization for my curve, and the curve's say oriented. So I know the direction of travel, I guess. Then to compute the work, then it's basically just this path integral or line integral, however you want to call it. Here they've called it a work integral to sort of drive home the fact that you're calculating the work done. Now here's some three basic steps to evaluate the work integral along a smooth curve. Take these steps. Well, essentially calculate this, calculate the derivative, and dot these two things together and integrate. Now I've kind of left off a step there, step 0. Anybody know what step 0 might be? If I've got a curve, what would... Yeah, got to parameterize it first. Okay, so step 0 in here would be parameterize C via some sort of smooth parameterization R of t. Okay, when I say smooth, of course, I mean a vector function that has a derivative that's continuous and never the zero vector. Okay, so step 0. Now, if you've studied physics, you may sort of look at this and go, well, come on, Chris, shouldn't there be a negative sign out there, out the front? This is sometimes taught in physics. Well, you can have a negative sign there under, for example, the following condition, right? This isn't in your notes, but it's not super important, okay? Suppose F is a gravitational field and you're moving a particle against that gravitational field. So instead of the force sort of working with you, it's kind of working against you. The work required to move the particle against, say, a gravitational field, you'll just put a minus sign out here. But that's not going to be too important for our study. All right, so let's do an example. Now this is a good example. fairly standard. We essentially want you to calculate the work done by this particular force in moving a particle from a point, the origin, to this point. So let's call the origin, say, point A, and call the end point, point B. For this, what we need to do is parameterize the line segment in the forward direction. Okay, so if I've got my three-dimensional setting here, this might be a reasonable picture. And essentially you start at the origin and you move along the straight line in sort of this direction and stop at this point, I guess. Okay, so A is just the origin here, big A. Okay, so the first thing we need to do is parameterize, find a smooth parameterization, a way of describing our curve. So let's parameterize. So let's call this C. Now, we looked a little bit at parameterizing lines and line segments in week 1. But I still think some people are a little bit confused about the derivation. So let me show you how you can parameterize this, this line segment. Okay, so we use a vector valued function of one variable, and I'm going to use basically the following. Okay, kind of like the position vector of the starting point times 1 minus t, plus t times the position vector of the finishing point. Now, some people are still a little bit confused about how you derive that. Well, if I have time at the end, I'll give you a few more details of how that comes about. Okay, it's not super difficult. It just requires the equation for the line through the point, through the vector. Sorry, AB.
Is there any particular reason why you favour that over the point and then the vector in the direction towards B?
Well, it's one and the same, really. It's one and the same. It's just written a slightly different way. Okay? Yeah. So, and you'll see that if I have time to do the derivation. Okay? That's a good question. So from the setting that you were talking about, you will come up with this. Okay? I mean, this is just the way I remember it, to be quite honest. Okay, so the vector OA, well, A is the origin, so of course the position vector of the origin, well, that's just the origin. And OB is just going to be the following vector. Now, if I multiply through here, of course, I'm going to get 0. So this is going to be my parameterizing function, or my vector function that describes C. Okay, so what do I need now? I need to take my vector field and I'm going to evaluate F along the curve. Okay? So along my curve, my vector field is going to be the following. Well, think of, this as your x, your y, your z. So I'll go up here, I'll replace x with t, y with t, and z with t. Now, of course, if I wanted to write this out as a triple, I could write it like this. Okay, here I've used I, j, and k, but in this course I sort of switch between the two, sometimes to save a bit of space. Okay, so let's go up here and sub in t for x, t for y, so I get t squared there, and t for z, so I get t there. Now, what I want to do is take that bottom line and dot it with the derivative, the tangent vector of my curve C. So let's compute the derivative here. So to compute this derivative, I just differentiate the components individually. So it's going to give me 1, 1, and 1 when I differentiate with respect to t. Okay? So, the work done is just the following line integral. If I write it out in terms of my t, it's this, which is actually what we're going to use to do our computations with. Now, a and b are derived from the t interval. So a is going to be 0 and b is going to be positive 1. Okay, so that is and r dash is that. So when I take the dot product, I'll get a function of t and a reasonably simple integral, hopefully. So when I take the dot product, I'm going to get t times 1 plus t squared times 1 plus t times 1. So it's going to give me 2t plus t squared dt. So let's integrate that. Which is going to give you 4 on 3. Okay, so that is a good example on work. Here's another kind of application with integrating over curves called the flow integral. The flow integral. Okay, so suppose you've got some sort of curve and you've got a smooth parameterization for it, and your vector field f is, say, is continuous, it has continuous components, right? We speak of the flow along the curve given by this line integral or path integral, however you want to call it. Okay? Now, to put this into some sort of context, suppose you've got a velocity field of some fluid and it's flowing through a region in space like a hydroelectric generator. Now, what the flow integral does, it measures how much the velocity field kind of lines up with the curve involved. Okay, so what is the tendency of the fluid to flow along the curve? How much does it line up with the curve? Is it a strong match or a very weak match? Okay. If the curve C is a closed loop, like a circle or an ellipse, then the flow is called the circulation around the curve. Okay, and we talked about circulation density last week when we were looking at the curl, the scalar curl. Okay, so there's nothing really that much different here. It's just, remember, you know, an integral over a curve. So it's nothing new. It's just sort of given another name in a different context. Okay, so along, say, a curve C. Now, if we have a closed loop, sometimes we use the following notation. We use this integral with a little circle in the integral sign. That means that you're integrating over a closed a loop like a circle or an ellipse or something else. Okay? So when you see that, you know that your curve is a closed curve. Okay. So let's look at a simple example again. Here I've got a vector field. We're just working in a plane here. So if I wanted to write this out in terms of I and j, I could. We're asked to calculate the circulation of this vector field around a circle with radius a and centre at the origin in an anti-clockwise direction. Okay, so let's just draw a basic picture. Here's my curve. Essentially what we're asking in this question is how well does the vector field line up with that curve? That's essentially what we're calculating. Okay, so let's parameterize. So we want to sort of go this way. So parameterize C. Who can remember how to parameterize a circle with radius A? What would we use? Yep, A cos t, comma A sin t. And what we want is, as t increases, we want the sort of the vector to sort of point and rotate this way, not the other way. So that would actually be okay. Right? Now, what we're going to do is, I'm just going to calculate the derivative. So if I calculate the derivative by calculating the derivatives of each component. And basically you want to take that derivative and dot it with the original vector field around C, evaluated around C. So along C, F will be the following. So imagine this is like your X and this is your Y. So you go up here, you replace X with A cosine T and Y with A sine T. So I'm going to get something like minus A sine T and A cosine T. So all I really need to do now is dot these two things together and integrate them from 0 to 2 pi. So the circulation, let's just call it circ, just the following. Now, I'm also going to put a little arrow on that circle in the integral sign to show that I've oriented the curve in an anti-clockwise direction. So let's, this will be my A and B. Let's work this out. So it's going to be sine t, A cosine t, dotted with this vector here. So I want to integrate that dot product. So if I expand, look what's going to happen. I'm going to get A squared sine squared t plus A squared cosine squared t. Ah. So now you can see, of course, cosine squared plus sine squared equals 1. So it's just this. Let's go with that. Now, what does it mean? What does it mean? Well, the larger the number, the stronger the alignment between F and the curve. Okay? The curve C. How do we measure that alignment? Well, we can graphically illustrate it. Here's my R vector, my position vector. there's my unit tangent vector, and if you draw in this at, say, any point, it's actually going to lie along the tangent vector. So you can't get a better match than what we have, because at every point on that curve, the vector field actually lies along the tangent vector. Okay? It just comes back to the dot product between this and this. Okay? Questions? Questions? Okay. Okay, here's another important application of these line integrals, so-called flux or flow rate in the plane. Okay, so suppose I've got a region that's sort of bounded by a smooth curve. And let's say the F vector is, say, the velocity field of a fluid. Okay, so there's fluid moving in the plane. Suppose I want to measure the flux sort of out of that region, that enclosed region. How do I measure it? Well, we spoke a little bit about this when we looked at divergence, but essentially what I do is, say I'm at a point here, I can formulate a unit normal, say an outward pointing unit normal if I want to calculate the outward flux or the outward flow rate. And at that point, at every point on the curve, you know, F's going to have some value. So essentially, what this flux, how you produce it using line integrals is the component. It's basically the integral of the normal component of F, just integrated around the curve. That's what that F dot n hat means. Okay, so think of this little triangle, this length here. That's, in this case, because n hat's a unit vector, that length is going to be F dot n hat. Think about, there's going to be some function. Think about integrating that over the curve. That's what you're doing.